All right, well, hey, welcome to another wonderful day here in differential equations land. So today's plan, we're going to talk a little bit more about the second order differential equations. We'll talk a little bit more on the theory involved. And we'll start looking at probably finding some solutions to some really basic ones. I mean, obviously you saw that with the first order, there were all kinds of different techniques depending on the form of the equation. I'm sure it's going to come as no surprise to you that the same thing's going to happen with second order. But we're going to start easy. We'll start homogeneous, and we'll start with functions that are just constants and things like that. But that will help us when it gets time to be dealing with more complicated things. So I'm going to do that, and then we should have some time at the end of class to talk a little bit about the exam that's coming up on Friday. So that's my plan. But before I do that, how about you guys? Any questions on the homework? Anything that we've talked about so far that you'd like to get to have some questions on or get some refresher on? All right, well, I'm not hearing anything and I'm not seeing anything in the chat box. So then we're going to go ahead and move forward. So I'm going to hop up to the whiteboard and I'll be right back with you. All right, so we're talking about second order linear differential equations. And we started hitting at what kind of functions we should expect to be solutions and things like that. And I want to talk a little bit more about the theory, about when we know we've got solutions, what we're looking for in terms of solutions, because things get a little bit more complicated now that it's second order. But let's just start with, we're going to go with linear, second order, homogeneous. All right, so we've definitely narrowed it down. Second order, there's y double prime. Linear, okay, so there's no y squared, just square roots of y or sine of y or anything like that. And homogeneous, equaling 0. So these are going to be the ones that look like this, where we've got our y double prime plus p of x times y prime plus q of x times y equals 0. So we talked about just in general the linear second order, but this time let's make them homogeneous. All right, so this is equal to 0. So this is what we're going to look at first. We're going to look at this kind of differential equation, which, I mean, to be fair, if you go back and look at what we did for first order, it's where we started. We started with first order linear homogeneous, and then went to non-homogeneous and non-linear. Right? Okay, so same deal, we're just kind of bigger. Now, something that I mentioned last time, and is definitely a theorem, so let me just remind you about that, is that if p of x and q of x are continuous, then there's a unique solution. And this is very similar to what we saw for first order. It's just now we have two functions we have to worry about, both p and q. And when I say here they're continuous, remember that means they're continuous on some interval, a to b, right? And then when I say a unique solution exists, that's to an initial value problem. And that's on a subinterval of the other. I just don't want to write out all the technical stuff, but this is definitely something that we know is true. All right, now I want to add to this. I want to give us some more theorems that are going to help us when it comes time to finding solutions and creating solutions. And for those of you who took linear algebra, and I'm actually just curious, is there anyone here who didn't take linear algebra? Just give me a real quick yes or no in the chat box if you did not take linear algebra. Okay, so you guys have all seen linear algebra. Well, then let me just tell you what we're going to do, at least on the start of today. Oh my God, it's exactly linear algebra. You're going to really see the connections. And I know that, Victor, you've been seeing this a lot as we've been going, or at least you've been bringing it up a lot. You're going to see a lot of tie-ins to linear algebra today. All right, so here's our next theorem. So this one's new, but this just says that if y1, excuse me, and y2 are both solutions, then if you take a linear combination of them, that is also a solution. Okay. So in the language of linear algebra, that means that this differential equation is a linear operator. Okay. So I imagine Larry mentioned those at some point, but basically that's what this is saying. Now, the proof of this is pretty easy to see. If you just put this in as a potential solution, right? So we say, let's let y equal c1 y1 plus c2 y2. So then y prime is c1 y prime plus c2 y prime. And y double prime is similarly c1 y1 double prime plus c2 y2 double prime. Okay, then take those and put them in here. Put them into the original differential equation. So you're going to get the second derivative plus p times the first derivative plus q times the original function. If you distribute and then bring together all the ones that have y1s. So we're going to get a c1 y1 double prime plus p times c1 y1 prime plus q times c1 y1. And then you're going to see exactly the same thing, but with the 2's. Well, the first set you can factor out as C1. The second set you can factor out as C2. So after doing a little bit of algebra, we get here. But now that we're here, oh, this is beautiful. Look at the bits that are in parentheses. All right. If you look at those two things, those are both equal to 0. Because y1 and y2, they were solutions to this differential equation, which means when you plug in y1, you're going to get 0. And when you plug in y2, you're going to get 0. And that's exactly what those two things are. Okay, so both of those are 0, which means 0 times your favorite c's are also equal to 0. So there's your proof. We know for sure that with linear second order homogeneous differential equations, stacked without that many classifications, But we do know there that if you take any two solutions and you form a linear combination of them, that's also going to give you a solution. All right, so cool. This is a linear operator. That's actually nice. We like things that are linear operators. They make life easy for us. For example, like just plain old integration, plain old differentiation, those things are linear operators too. Right? Okay, so there's your new theorem. We can take any combination, put them together, and solutions, combine them, and we'll get another solution. All right, so here's your next theorem. Actually, this isn't a theorem. This is just going to be a definition. All right, so we'll put a DFN for definition. All right, we say that Y1 and Y2 form a fundamental set of solutions if all, keyword all, solutions can be written as a linear combination of them. So this is very related to this theorem, but I want to point out the difference. The purple theorem says if you have two functions or two solutions to the differential equation, that any linear combination of them is also a solution. This in green, we're requiring that all the solutions can be written as a linear combination of these guys. And that can't always happen. There are circumstances where you can have two different solutions to a differential equation, but there are other solutions that can't be written as linear combinations of them. Okay, so let me give you some linear algebra terms. So if you go back to your linear algebra, this is saying that Y1 and Y2 are a spanning set. All right. So again, this is just from linear algebra. So in differential equations, we'll call them a fundamental set of solutions, but it really just means that there are solutions that span the set of all solutions. I'm hesitant to say solution space because we haven't proven that it's a vector space. Okay, so when I say fundamental set, this is what I mean. It's a set of functions that actually spans the solution set. Okay, so really our goal is going to be to find a fundamental set of solutions. Because if we've got a fundamental set of solutions, we can just then take linear combinations of them, and we know for sure we've got every solution out. So again, to go back to linear algebra words, we're trying to find a basis, right? We're trying to find a spanning set. The linear independence, we'll see here in a second, the need for linear independence. But we're kind of halfway there to getting a basis, right? Is for it to be a spanning set. All right, so linear independence. How are we going to show that? How are we going to show that that's a requirement, that we actually need linear independence? Well, we're going to do that in kind of a roundabout way. Let me introduce you to this thing called the Wronskian. Now, the Wronskian, there's a Wronskian and there's a Wronskian matrix. I'm actually curious, did you guys see these in linear algebra? Sometimes they pop up.
I really think we did.
You recognize that name?
Yeah.
Yeah. Okay, so we're going to look at the Wronskian here because it's kind of a big deal. But first of all, there's the Wronskian matrix. Okay, so it's Wronskian, Wronskian, named after a guy whose name I think was Wronski, last name was Wronski. So the Wronskian matrix, what it's going to hold in it, in this case, it's going to be a 2x2 matrix. And it's going to hold the y1 and the y2 in the first row. And then the second row is going to be y1 prime, y2 prime. And those y1 and y2 are going to be our fundamental set. And basically, we're going to use this to see what requirements there are for y1 and y2. So this is the Wronskian matrix, but the Wronskian itself, we use the letter W for that. It's y1 times y2 prime minus y1 prime times y2. Hold on, I've got that. No, that's right. Never mind. I thought I had a subscript wrong somewhere. But if you recognize this, I want you to notice that this is actually just the determinant of the Wronskian matrix. Right? If you take that 2x2 matrix and you find its determinant, that's what the Wronskian actually is. Okay, so there's this thing, the Wronskian. So the question is, where is this coming from? Why does it matter? How does it pertain to what we're doing? Well, let's come back to this linear second order. But let's add in an initial condition. All right, so let's say that we had in here as well an initial condition. And so I'm going to have, say, y of x naught equals y naught. But remember, for the second order, we need to have some other piece of information. So let's say we also know that y prime of x naught is equal to y prime naught. We'll just call that. All right, so let's say we've got this initial condition. Let's look at solutions that are linear combinations of the fundamental set. So we're going to go with a fundamental set, y1 and y2. All right, so we already just saw that when you got a fundamental set, you know that your solutions can be written as linear combinations of them. So we'll go ahead and call those y is c1 y1 plus c2 y2, which of course means the derivative is going to be c1 y1 prime plus c2 y2 prime. But let's apply.
I have a quick question for you.
Sure.
When it means fundamental set, it means they're linearly independent functions.
We haven't proven that yet.
But yeah, it is.
We're going to see that that is a requirement of them. Yes.
Okay.
Right now, all we know is that they are a spanning set.
Okay.
But this is going to show that they have to be linearly independent.
Okay.
And then because they span and are linearly independent, they will be a basis for the solution space. So we're almost there. We're almost there, Brian. Okay, so let's think about our initial condition. If we take those initial conditions and we put them in here, what that's going to do, well, that's going to make it so that C1y1 plus C2y2 is equal to y naught. And C1y1 prime plus C2y2 prime is going to equal y naught prime. And I can actually write this as a matrix equation. So we get y1, y2, y1 prime, y2 prime times C1, C2 equals y naught prime. Okay, so here now is all of a sudden where you go, oh, there's the Wronskian matrix. That's where it even comes up. I mean, the fact that someone was able to name that after themselves, okay, good on you, I guess, but I just want you to notice that that's exactly what this is, right? That's the Wronskian matrix. All right, so let's think about the situation where solutions exist, because obviously we're looking for where solutions exist. What we saw is that when P and Q are continuous, that we're guaranteed unique solutions. So let's think about that situation where P and Q are continuous. So that means there has to be a unique solution. That means that this thing, there has to be one and only one of them, which means there has to be a unique solution to this matrix equation. Okay, well, if you go to that, remember that the following are equivalent list that you formed back in linear algebra? On that list, that like huge long list, on that list was unique solution to matrix equation. But there was also on it that the inverse of this matrix has to exist, which also had on it that the determinant of this matrix could not equal 0. Okay, so that's why all of a sudden we care about the Wronskian itself, right? So what we know is that for this to be to have a solution, a unique solution, we need W cannot equal 0. The Wronskian itself cannot equal 0. Okay. Well, also on that, the following are equivalent list, there was something about linear independence, linear dependence, right? And using that actually leads to, not only does W not have to equal 0, but that also gives us that y1 and y2 must be linearly independent. So it's good that you guys all took linear algebra, because a lot of these things that I'm now saying and referencing, you can tie back in and go, oh yeah, I remember seeing that. And that's why I mentioned at one point that sometimes there are schools that teach these both together, linear and differential equations, because they definitely go hand in hand when we're talking about the theory of differential equations.
That'd be rough.
That'd be a pretty crazy class, huh?
Yeah.
It's usually a semester class. So think about what we do in 2 quarters, doing it in 1 semester, be a little bit compressed. But yeah, that'd be pretty crazy. That was not what it was like in my school. Where I went, they were independent classes. All right, so I guess that gives us another theorem. We can say that the fundamental set, or that the fundamental set exists if the Wronskian is not equal to 0, right? But I don't think we need to write it up as a theorem because it's really just tied into the following are equivalent stuff. But it turns out we can actually, given a differential equation, we can figure out what the Wronskian is without creating the fundamental set. And this is another theorem. This one we'll go ahead and put up here, but it's named. And it's called Abel's theorem. I know you might see that and think Abel, but it's pronounced Abel. He was German. But Abel's theorem. And what Abel's theorem tells us is that the Wronskian itself is going to equal e to the integral of negative p, and I'm going to go ahead and put here dx because that's our variable right now, but it can be a t or whatever. So basically what this is all you want to know is what the Wronskian is. It's going to equal some constant times e to the integral of minus p. So we'll know the Wronskian at least up to a constant multiple. All right, well, let me show this to you. Let me go ahead and prove this one because the proof isn't hard. And it's good to have it. So remember what the Wronskian was, right? It was that determinant of that matrix that held the solutions y1 and y2. So it was y1 times y2 prime minus y1 prime times y2. Okay, now just for the hell of it, just trust me on that. Let's find w prime. So you take the derivative of w, and you're going to get y1 prime y2 prime plus y1 times y2 double prime. This right here was the product rule on the first piece. And then you do the product rule on the other piece, you get y1 double prime times y2 minus y1 prime y2 prime. Right. So again, this was the product rule on that piece. But in here, the first and the last terms cancel. Those guys are identical. Y1 prime times y2 prime, they're being subtracted. So the derivative of the Wronskian actually simplifies to y1, y2 double prime minus y1 double prime times y2. All right, so it is what it is. All right, now let's go back to the differential equation and let's think about when y1 and y2 are plugged in. So we're going to have y1 double prime plus p times y1 prime plus q times y1 equals 0, and y2 double prime plus p times y2 prime plus q times y2 equals 0. That's what y1 and y2 are, right? Well, they are solutions to the differential equation. So we know that this is true. So we're going to take this system and I'm going to multiply the first one, the first equation here, by negative y2. And the second one, I'm going to multiply by y1. And then I'm going to add them together. Good old elimination kind of stuff. Okay, so these first pieces, we're going to get y1 times y2 double prime minus y2 times y1 double prime. That was those two. The next two, I can factor out a p. And I'm going to get y1 y2 prime minus y2 y1 prime. Okay, so that was those two. And then the q's, notice that those two are just going to go away. Because we're going to get a positive y1, y2 times q. And the other one, we're going to get a negative y1, y2 times q. So those are gone. So you're probably asking yourself, why did Bruce just do that? I mean, yeah, we got rid of the q's. Big deal. Well, take a look at what's in those parentheses. The second one, that's the Wronskian. y1 times y2 prime minus y2 times y1 prime. The one in the first parentheses, that's w prime. Right? y1 times y2 prime or double prime minus y2 times y1 double prime. So this thing turns into w prime plus p times w equals 0. So now we've got a first order linear differential equation. And we know how to solve those. Right? And so if you solve this, by this point, you're probably recognizing solutions to this form. I hope you are. But what we end up with is c times e to the negative integral of p dx. Oh, yeah, right there. Ta-da. All right, so basically, what this is telling us now is we know what the Wronskian is going to look like, which can help us. Because remember, we know that the Wronskian can't equal 0 if we want to have solution set. So you can actually take one of these things. You can take a differential equation of this form and know right away whether or not you're going to get a unique solution or where a unique solution can occur without actually finding the fundamental set. So let me show you real quick what I mean. Let's do a kind of a simple one here. Meaning, let's say we've got like y double prime plus 3y prime plus xy equals 0. Okay, so I have no idea what a fundamental set of solutions is to this. Right? I don't know my y1 and I don't know my y2. However, I can calculate my Wronskian. My Wronskian is going to look like this: c times e to the minus 3 dx, which is going to give me c times e to the minus 3x Okay, so let's look at this thing and think about where is it 0? So what x values will make this 0?
There isn't one.
Yeah, good. I was gonna say, don't fall for the trick. It's exponential. We know exponentials are never equal to 0, right? So if we look at this, so no x makes this 0. All right, so what does that tell you? This tells me then that there is a unique solution for any initial value problem. There are no x's where there's ever going to be an issue. Right? It also tells me that whatever my fundamental set of solutions are, they're going to be such that the Wronskian gives me e to the minus 3x. Well, that even tells me a little bit about the structure of these things. Right? Like think about the Wronskian, how it's formed. Right here. To get e to the minus 3x, that tells me at least one of y1 or y2 has to have an exponential piece in it. In fact, it's going to have an e to the minus 3x. It might just be plain old e to the minus 3x for all I know. But I know that's going to have to show up in order for the Wronskian to look like this. So take Abel's theorem for what it is. It's a really quick way to figure out what the Wronskian looks like that you can then use to help you determine where solutions are going to be good. But also, it can help you make your guesses for the y1 and the y2s. Right? So you might go, well, e to the minus 3x, let me try it. If it works, awesome, it's part of your fundamental set. If it's not, maybe try x e to the minus 3x. Right? It at least gives you an idea of where to start. Instead of the infinite number of possible functions, we're now on that smaller infinite number of functions that are related to this. Okay, so there's a little bit more about the theory here. And again, to kind of tie this back to linear algebra, what we're doing is we're finding a basis. And it's always going to require two functions. All right, so at the end of the day, this is what we really need to know about when it comes to finding these things. Right? We need to find a fundamental set. And it's going to be of two linearly independent functions. All right, so our goal is going to be find those two. All right, so let's try it. Let's see if we can actually find some solutions, keeping in mind that we're going to have to find two that end up being a spanning set. All right, and so it's good enough if you find two solutions that are linearly independent that will form a basis. Again, that comes back from linear algebra. You may remember, right? If you find a set of vectors that's the same size as your dimension, you're good to go. Well, the dimension of these is 2. So if you can find two linearly independent functions that are solutions, you're good to go. In fact, let me not put functions here, put solution.
And that's because it's second order?
Yep, no, it's because it's second order. So first order, we only had to find one. And you may remember all of our things, it was whatever that function is, times c plus c, like whatever, right? There was always just the one function. Now we're going to go to 2. If it was a third order, your fundamental set's going to have 3 in it. Fourth order, it's going to have 4, and so on and so forth. Okay, so higher order is going to end up, like when we get to higher order a little bit further down the road, you're going to go, oh, this is exactly what we did when we had second order. We just had to find more of them, because that's exactly what changes. It just increases the dimension, so it increases the size of your fundamental set, which means you need to find more functions. All right, so let's do this. Let's actually refine our type of differential equation to an even smaller set. Okay, so now we're not going to just look at linear second order homogeneous, but let's look at those that have what we say constant coefficients, meaning P of x and Q of x are constants. So that means that what this is going to look like then it's going to look like a quadratic equation, just without powers of y, we've got higher order derivatives of y. But that's what I mean by this kind of differential equation. So constant coefficients just means the multipliers on all those things are constants. All right, so what I want you to do right now is tell me a kind of function that you think could potentially be a solution here.
Polynomial of degree 3.
Okay, so let's go back because we kind of hinted at these before. So Bradley, you brought up polynomials before, right? And I definitely like how you threw on a degree there. But I think degree 2 might, or degree 3 might be too big. Because let's say there's an x cubed in your y. That means there's an x squared in your y prime, which means there's an x in your y double prime. And there's, you know, that might not work out so well. And then even think about that. If there's an x cubed in your y, there's never going to be any other x cubed that cancels out later. So polynomials, while they do give you more polynomials, if all we have are constant coefficients, that's not going to quite cut it for us. I see Ralph put in the chat box 0. Okay, you're lucky we're not in class together because I would chuck something at you. Of course, 0 is. 0 is a trivial solution, right? When we're talking about homogeneous, homogeneous always have a solution of 0, but we don't care about that. We care about the other thing. So let's think about some of the other functions that we talked about last time. Sine and cosine.
Exponential functions.
Right, exponential functions. Those both, sine, cosine, and exponential, both have a shot at doing this. But probably the most basic and the easiest to try would be some exponential form. So let's try this. Let's make a guess. And we're going to guess y equals e to the rx. I'm putting the r there because I want it to be able to be, you know, anything. I want to make it a nice generic exponential function. I'm not worrying about any kind of a scalar multiple out front because I know the scalar multiple doesn't actually matter. It's just going to go along for the ride with all these, which means I could factor it out and just divide it into the 0 anyway. So, but let's just go with it e to the rx as our guess. Well, let's see what that means R has to be in order for us to have a solution. All right, well, if y is equal to r e to the rx, then y prime is r e to the rx, and y double prime is equal to r squared e to the rx. So let's put those in and see what that forces onto our r. So I'll come over here. So if I put those into the differential equation, I'm going to get a times r squared e to the rx plus b times r e to the rx plus c times e to the rx. And I want that to equal 0. So let me factor out the e to the rx. Okay, so we're here. Now the e to the rx, that's never 0. It's an exponential function, right? Those things are never 0. Which means if this is going to be a solution, I need to have ar squared plus br plus c. That has to equal 0. So we give this thing a name. We call this the characteristic polynomial. Okay, so it's just ar squared plus br plus c. And basically, we're just going to look and see where is that thing equal to 0. We solve that for r. That tells us what kind of numbers we can put in here for our exponential. And, oh, hey, check it out. We're getting solutions. All right, so let me show you an example. These are actually kind of fun. They're super easy to do. Once you do about 3 or 4 of them, you're not going to have to think about them ever again. They're super fast. All right, so here we go. Let's try this one. Let's say we add y double prime plus 4y prime minus 5y equals 0. All right, so it's linear, second order, homogeneous with constant coefficients. So that's exactly the kind we're talking about right now. Okay, so here's what we do. We first create our characteristic polynomial. So it's going to be 1r squared plus 4r minus 5 equals 0. Now this one is nice. It factors. Yeah, r plus 5, r minus 1. And so we get 2 different r values. R equals minus 5 and r equals 1. All right, so if we go back and we look at, remember what our guess was. Our guess was e to the RT. So this one suggests that a solution would be y equals e to the t. And the minus 5 suggests that there's a solution of e to the minus 5t. Now, I'll leave it to you if you would like to check these two against the differential equation. I'm not going to bother because we already showed that things that make this polynomial 0 will be solutions when we did all this stuff over there. So I'm not going to redo the work. All right, well, I just found 2 solutions. All right, well, I know that linear combinations of these are going to be solutions as well. But the last question is, are these things linearly independent?
Yes.
Well, we hope so, right? So Bradley, you were pretty confident with your yes there. Why are you very sure?
There's nothing I can multiply to either of those to make them the same.
Okay, so when we're in the two-dimensional world, right, we know linear dependence means one's a multiple of the other, and that clearly isn't the case here. So they are a linearly independent set, which then means that they are a fundamental set. So that means I can write my solutions to the original differential equation as linear combinations of these. Because we can call this, say, y1 and y2. Go ahead and do that real quick. So since they're solutions, we've already proven that linear combinations of solutions are solutions. So this is also a solution, but this covers it. All solutions of this original differential equation have this kind of form. And the C1 and the C2s are going to change depending on our initial conditions. But there's your solution. All right, I mean, fast and easy, right? Seriously, that's all you got to do is find the zeros as polynomial? Yeah, seriously. That's all you got to do. Right? Now, are they always going to be this nice that you can just factor it? No. Are you have to use a quadratic formula? Sometimes. Right? But regardless, this is the process. If you look at the Wronskian, let's just look at the Wronskian real quick. If we make that matrix, e to the minus 5t, e to the t, we then need the derivatives, which are minus 5e to the minus 5t, and then e to the t. And if I take the determinant of this, I get e to the minus 4t plus 5, e to the minus 4t, or 6, e to the minus 4t. And you can see that it's never 0. And in fact, if we'd used Abel's theorem, remember what Abel's theorem says is that the Wronskian is some multiple of e to the negative integral of p. Yeah, we knew going in from Abel's theorem that we had to have a Wronskian of e to the minus 4t. Look, it worked. Okay, so all of this stuff that I just did in the green and the little Abel's theorem side, those were not needed in order to find our solution. I just wanted to tie it back to what we were talking about. All right, so pretty easy, right? Like, what's going to make this hard, do you think?
Polynomials that aren't nice factoring.
Okay, yeah, so the ones that that you can't quite factor, or you know, that kind of stuff, definitely going to be uglier. But they're still going to be done exactly the same way, right? Let's just do one real quick, and you'll see that it's not that terrible. It's just a matter of taking care of business. So let's look at another one here. Let's say that we've got y double prime plus 5y prime minus 2y equals 0. So that one doesn't factor. So we make our polynomial. We're going to get r squared plus 5r minus 2 equals 0. So we go to our quadratic formula. -5 plus or minus the square root of 25 plus 8 all over 2. So we get -5 plus or minus the square root of 33 over 2. Okay, yuck. Sure. But here you go. Here are your solutions to this differential equation. You get C1 times e to the -5 plus root 33 over 2t plus C2 times e to the -5 minus root 33 over 2 times t. So what? It's different. I mean, those are still numbers. They're perfectly fine numbers. They just don't feel as nice as -5 and +1. All right, so really it just comes down to, can you find the zeros of this polynomial? If yes, you're good. Okay, well, yeah, of course we can. They're quadratics. We know how to solve quadratics. Where this is really going to get difficult is when we go higher order, because you can then just imagine, like, what if this had been like a 5th order? If we extend this idea, it's going to lead to a 5th degree polynomial. That's where they're going to get challenged. Okay, but it's not quite as simple as I just portrayed, because let's look at something like this guy. Let's say we've got y double prime plus 2y prime plus y equals 0. So we make our polynomial, r squared plus 2r plus 1 equals 0. Turns out that this one does factor. It's r plus 1 squared. And we get r equals -1. Okay, cool. Super easy, right? So that tells me that a solution is e to the -1t. So e to the -t. All right, so that's half of our fundamental set. Uh-oh. Why uh-oh?
You only have one. You should have two.
Yeah, shit. I need 2. Fundamental set has to have 2 functions in it. And I just got 1. And there's no way to get a second one from this polynomial because there was only one place where that equals 0. And that happens sometimes with quadratics, right? Okay, so Ralph, you just said, oh, should it be c times e to the -t? No, it's not a should it be, it's a could it be, yes. All I need is a solution. So e to the -t is a solution. When I go and I form all the possible options after I get a fundamental set, then yeah, I'll definitely multiply that by a C1. But just as one of the elements of the fundamental set, you don't need to put a C on there. You can if you want, but you don't need to. And because you don't need to, I don't. Because I'm late. Okay. Well, shit.
Or maybe we could go to the Wronskian matrix.
Okay, maybe. Ooh, Wronskian to the rescue?
Yeah.
Maybe. All right. Well, I desperately need that y2 though, right? Because if I'm going to write my fundamentals or my solution, I need to have both of them. Turns out we're not going to use the Wronskian, although we could. We could use the Wronskian to help us figure out what kind of form would help. instead, let's do our other really famous trick. What other trick do we do a lot now when we've got a solution, we're looking for something else?
Pretend like we know another one.
Yeah, how do we do that though? Like, what has been the general thing that we've done? Anytime we've had a y1, we want to make a guess of something else, what do we do? What I'm getting at is we're going to use an integrating factor. We're going to multiply. We're going to say, you know what? Let's say, obviously we don't know what y2 is, but let's say that y2 is some multiple of y1. Because then maybe we can figure out what form that u has to be. So let's try it. Let's just say that y2 is going to be some multiple of e to the minus t.
I have a quick question for you, though. Does that ruin linear independence?
Well, not necessarily. Why are you thinking that? And it's okay to think that.
Because if we're multiplying by something times y1, then it's basically saying that we can write them as a linear combination of one over the other,
Okay.
which is linearly dependent.
But that's only true if this guy u is a constant.
Oh, if it's a function, that changes it.
Yeah.
Got it.
What if this is t times e to the minus t? Or
Then-
sine of t times e to the minus t?
Okay.
Insert your favorite non-constant function, then we're good. So you're definitely right that if you do this, and if we try this, and what we find is a constant u, we're gonna have to go, oh no, that doesn't work. Right? So it's good that you noticed that. It's just this thing u could be more complicated than just a constant function. And our hope is that it's more complicated. Right? And it doesn't have to be terribly complicated. Like I said, I'll be happy just with a t or a t squared or square root of t. I mean, it doesn't even have to be gnarly like a natural log or no, as long as it's anything but or something like that, I'm good. All right, well, let's see what that's going to force u to be if we come back and we look at our original differential equation. So y2 prime then is going to be u prime e to the minus t minus u e to the minus t. Right, product rule on that. And then we got to do the second derivative. So that's going to be product rule again. We're going to get u double prime e to the minus t minus u prime, or sorry, plus u prime, no, minus u prime e to the minus t. So the product rule on that first one led to these two pieces. And then we're going to get minus u prime e to the minus t plus u e to the minus t. And so these two pieces were the product rule on that guy. So let's put all that back into this differential equation and see what that forces onto our u. So we're going to take the y2 double prime. So that'll be u double prime e to the minus t minus 2 u prime e to the minus t plus u e to the minus t plus 2 times the derivative. So u prime e to the minus t minus u e to the minus t. and then plus the original function, which was u e to the minus t. We need that to all equal 0. All right, so let's combine things here. First, we can factor out an e to the minus t. So I'm just going to pull that all the way out because it's part of everything. And then I'm going to group them according to their the derivatives. So we've got u double prime, and that's the only one. For the u primes, I've got minus 2u prime and a that 2 shouldn't be there, and a plus 2 u prime. So those things cancel out. And then if I go to the u's, I've got plus 1 minus 2 plus 1. Well, those all cancel out also. So once I simplify that all down, what I've got is e to the minus t times u double prime equals 0. All right, well, like we saw before, e to the minus t never equals 0. So in order for this to be true, whatever u is, its second derivative has to be 0. All right. So give me a function whose second derivative is 0.
Any polynomial squared, right? No, it's the first.
You went 1 degree too far.
Yeah, the
If
first.
we integrate it, so then u prime is some constant. If we integrate again, u is that constant times t plus some other constant. So what I need is for u to be a linear function. And I can actually pick any linear function I want. Right? Because all I need is that the second derivative equals 0. So give me a really good linear function to make u equal.
T.
Beautiful. How about we just go with u equals t? So we're going to pick u equals t. Why? Because I need one. And that's the easiest one there is. All right, so we can erase that question mark on y2. And so y2, we know, here is another function that is a solution to the differential equation. Right, we built it. But I know for sure that these things are linearly independent because they're not scalar multiples of each other. So here you go. Here is the solution set to this differential equation. Now I'll put the C1 and C2 on there, Ralph. So we're going to have C1 e to the minus t plus C2 t e to the minus t. Every function that satisfies this differential equation has this form. Okay, so yes, it is as easy as finding the zeros to that polynomial, to that quadratic. But we don't always have two solutions, right? I mean, go back to, remember quadratics? Sometimes you have two solutions, sometimes you have one solution, sometimes you have no solutions. Well, no real solution. Well, in the case where we have two solutions, it's super easy. take those two solutions, put them in as your powers, and you're done. It's these others that we have to develop some tricks. And so for the ones where you only get the one solution, like this guy, this integrating factor trick works beautifully. Right? And so we saw with this example that the integrating factor was just plain old t. So what we're probably going to want to do, not probably, but what we are going to do, is we're going to go, all right, let's do it generically. What if we don't pick a specific guy, but we do a generic root? Is there a way to figure out what that multiplier is in a faster way? But we'll do that next week, because I kind of want to spend some time to talk about the exam. So I think we're going to end here, but you're starting to see how, I mean, it's the same story as before. Recognize the pattern, do the things, and when in doubt, run an integrating factor. But the one last thing I want to show you real quick before we jump back down to talking about the exam. Check this out. If I factor out the e to the minus t, I get c1 plus c2t. And remember when we found our u, we saw that it had to be linear, and I even kind of walked through with some c's. There's your generic linear function times that e to the minus t. Crazy. All right. Well, anyway, so this is where we're going to pick up next week. We'll just run with this idea.
It's not always going to be linear, is it? The u?
U's do not always end up being linear. It totally depends on what's going on up in here.
Okay.
In terms of what it's going to look like for the specific constant coefficients where it's repeated roots, I'm going to save that for Monday. We'll go through the derivation and we'll see what that tells us and how we can then use the original form to tell us what the second guy looks like. But just like before, like think about the integrating factors you've run into in other places. Those integrating factors can take on all kinds of different structures. But it all comes back to what's our original differential equation look like. So I don't want to spoil that for Monday. All right, so I'm going to hop back down to my computer real quick, and let's just spend a little bit of time talking about this exam that's going to be on Friday. All right, I'll be right back. All right, so Friday's our first exam. First of all, in terms of what it's going to cover, it's going to cover up through chapter 4. Right? So it's going to cover chapter 1, chapter 2, and chapter 4, at least the sections of chapter 4 that we talked about. So things that you're going to have to be able to do. Let's just talk about what all those different chapters had. So chapter 1 was all about just sort of the intro, setting the table, and all that. So it was a lot of classification, right? It was the what is the order of this? Is it linear? Is it non-linear? Is it homogeneous? Is it not homogeneous? Right? That's basically what most of chapter 1 was. But we also did things like confirm that things were solutions, find the coefficients, so the solutions to initial value problems and that kind of thing. Really, well, and then we did direction fields. So really, here's what I expect that you should be able to do from chapter 1. Be able to classify differential equations. Tell me their order, linear or not, right? That kind of stuff. And then be able to draw the slope fields and be able to use slope fields to approximate curves, solution curves. Okay, so that's probably the big stuff from chapter 1 to go back and look at. Chapter 1 really wasn't much, honestly. It was chapter 2 where we really got into things. So in chapter 2, the big things, we talked about solving linear first order equations. That's what we started with. So those were the ones where if they are homogeneous, where they're equal to 0, you just do the e to the negative integral of p. And then if they are non-homogeneous, you start with the solution to the homogeneous. And then we had that method where we used an integrating factor to get us to the solution set thingy, but you get your u by doing the using the solution to the homogeneous, right? And then you integrate that thing and then multiply it by the homogeneous. So go back and look at your process for those, because I definitely expect that you should be able to solve linear first order, whether they're homogeneous or non-homogeneous. Okay. So that was one type that we did. Then we also looked at separable. The linear first order, at least the homogeneous ones, are separable, but separation of variables works for even more complicated, uglier things. And we saw that that works even for non-linear. So know how to do separation. I think most of you are probably pretty good at that by now. But definitely know how to do that, know how to solve initial value problems and the like. If I give you one, if I don't specifically say write it in explicit form, you don't have to solve it for y. Okay. Only if I say write it in explicit form do I expect you to go through and get to y. If you do that, if you have to do that and you get it in explicit form, be very careful, be very mindful, especially of like the square roots when you have the plus or minus. Because what in the end tells you whether you have plus or minus. What about a problem is going to tell you which of those to use?
The initial value.
Yeah. So always, if you're going to do it that way, make sure you go back to the initial value. Like I think we did one, remember, where it was on a circle, I think. And we had the plus or minus, and then we ended up going to the negative because the point we wanted was on the bottom half of the circle. Maybe I'm completely making this up. I don't know, but I seem to recall we did something like that. So use your initial conditions to help you figure out which of the options to choose if you're in that situation. But like I said, if I don't specifically tell you, you don't have to go ahead and solve it for y. Okay, so separation, that's a nice, easy one when you've got it. Also realize that there are times when you can do more than one method, and that's totally cool. If I don't specifically tell you a method to solve, to use when solving, do it however you want. You may remember there was, I think it may have been last time, maybe 2 times ago, where there was a one that we were looking at and we saw that like it was Bernoulli. We could use Bernoulli because it was a Bernoulli form, or it was separable. And I think we did it both ways, got to the same answer. Again, I don't care. Whatever you see, if you recognize it, go with it. All right. So speaking of Bernoulli, there were also a couple other forms that were related to separable because they end up becoming separable. And so one of those was the Bernoulli. Remember, the Bernoulli form has to have, it's got to start linear. So you got your linear pieces, the y prime plus p times y. And then that has to equal something times y to another power. Right, so that's a Bernoulli form. Many of them are separable, but if they're not separable, there's a technique that we talked about to make them separable. So we had those, and then we had the other ones that we called the homogeneous. Even though they weren't the same definition as homogeneous, those are ones you could write as y over x's. And again, if you've got that kind of form, function of y over x, there's a way to turn it into separable with the substitution. So we have that form. And then we also had exact. And I think that was like the last form that we really looked at in chapter 2. And the exact differential equations, those were the ones that
basically we find the potential function and set that equal to a constant. So know how to check those, know how to get the answer or get the solutions, but then also know the tricks that we had for when the two partials aren't equal to each other. And that's where we subtract them and divide by m or n and hope that they are a function of y or x individually. Because then if you're in that situation, again, you can find an integrating factor and go from there. So the biggest chunk of this test, and it's primarily all from chapter 2, was all the different techniques of solving first order differential equations. All right, so I would definitely review your techniques, but not just review how to do them, but review how to recognize which one to use. I think that's even more valuable, actually, because you can always look it up in a book, the steps, right? Like you can always type in how to solve Bernoulli equations into a computer and it will help you, do those steps. But you have to be able to recognize it and go, oh, that's one that's Bernoulli, or oh yeah, that's one that's exact, right? So I think it's probably well worth your time to just practice. Here's an equation. Which method or methods can I use on it? All right, so that's some recommendation I would give you. Yeah, so that was pretty much it in chapter 2. I mean, we also talked a little bit of theory in terms of when you're guaranteed solutions and when you're guaranteed unique solutions. Remember, by looking at the two functions, like when y prime equals something, that's something if it's continuous. Wherever it's continuous, you're going to be guaranteed a solution. And then when it's partial with respect to y is continuous, you're guaranteed a unique solution. So, but anyway, so from chapter 2, be ready to just solve differential equations and be able to tell me, where your guaranteed solutions and where those guaranteed solutions are actually unique. Okay, so that was chapter 2. Then we skipped chapter 3 because, as when Ralph asked, I was like, yeah, because it's computery stuff that I don't really find interesting and don't think really matters, but that's me personally, right? We jumped into chapter 4, which is now applications. So this is going to be the other big chunk of the test. There are going to be a bunch of applications. So just think about the different things that we talked about. We talked about growth and decay, but those are really easy. Got a super easy differential equation, right? Y prime equals k times y. And it leads to the good old PERT formula, right? Except we wrote it as CE to the KT, but same thing. But realize that we can adjust those things to get like logistic growth or whatever else. And those often, population things often end up being ones that are separable. But we also specifically talked about Newton's law of cooling. We talked specifically about when we have a carrying capacity, so logistic growth. Let's see, other ones we did. We did the pond problems, the mixture problems. And then I was like, there's got to be something else. And then we did the air resistance, right? We threw air resistance in there. Talked also a little bit about like what would happen with springs and all that, but we saw that like with springs, all of a sudden that leads to second order. So I'm not going to have you do anything like that. But anyway, so those are the big examples that we did, and expect a variety of those. But again, the important part to any kind of a word problem is going to be creating your differential equation. Because once you've got that, all right, now it's just look at it, figure out what form it's got, do the techniques to solve it. But this is really the same as any word problem, right? Go back to calculus, go to pre-calc, go to algebra. The hardest part of any word problem was sifting out all the information and creating the equation. Because then once you had it, you just did the steps. So this is something else I would practice, is given, you know, a word problem, practice setting up the differential equation. Even if you don't go all the way to solve it, at least practice getting them set up, because that's a really useful technique. All right, so that's what's going to be on the test. And I think if I asked you guys right now to make a sample test, your sample test is probably going to look a lot like my test. This isn't one that gets really crazy or super creative because it's very procedural, right? I'm not going to put anything on there that you haven't seen before. And I full on, oh, and by the way, I full on am okay with you guys just using technology to do the integrals and things, right? So if you run into something that's separable and you've got some gnarly function, feel free to punch that into Symbolab or your T89 and integrate. What I'm not okay with is if you just use a solve my differential equation. Okay, so what I'm going to expect to see, I want to see your steps in terms of, like, if you've got your differential equation, I want to see you manipulating it, whatever, doing it to get it into the form you need. Then if there's a little bit of calculus involved, okay, feel free. You can even write, use my T89 or whatever to get the integral. And then show me the steps going forward. Okay, so just make sure that you're showing me what you're doing. But in terms of actual integrals or derivatives, feel free to use your technology to help you out with those. Yeah, so I think that's all I've got to say about the exam. How about you guys? Questions, concerns?
What's the exam time?
Oh, okay. So the exam time, it's going to be 1 o'clock. I don't want to mess with that. So we'll have it start at 1, and then it needs to be uploaded, I think, by 3:30. Let me double check that real quick. I'm almost there. Yeah, 3:30. So it will be available starting at 1 o'clock. So if you go there right now, it'll give you the, like, it should say something like can't access or whatever. But it'll be available starting at 1 o'clock, and then you just have to upload by 3:30. So again, do me a favor, if you can, make it one PDF file that you upload through Canvas. But obviously, if you're having technical difficulties, worst comes to worst, just get it to me, email it to me, make sure I have it. Again, my intention for this test is that it's a 2-hour test. That extra half hour is to deal with technology. Okay, so this isn't a started at 1 and then, oh shit, at 3:25, I need to figure out about getting it uploaded. No, that's not the intention. All right, I mean, you can do that, but this is plenty of time for you to take it and get it to me. All right, so take it and get it to me by 3:30. But very good question, Bradley. Thanks for asking that. Other questions? I think by now you guys know me. You've all taken lots of exams with me. I mean, some of you have had me for like lots of classes. I think probably 5 or 6 for some of you. So you know what to expect. And yeah. So I think with that, I'm going to go ahead and stop our recording and wish you good luck. Oh, also just real quick. So there's no class on Friday, right? We're not meeting on Friday. Friday is just for you to take the test. Oh, the one other thing, if you need to make an arrangement for time, like I know some of you have testing situations with timing and all that, email me, let me know so we can get that nailed down. But other than that, good luck, and I will see everybody on Monday. So, oh, Ralph, yeah, you can send me emails during the test, absolutely. And I'll be checking them. I'll be checking off and on. It may not be a real quick response, right? Because I'll be doing other things, but I'll try to get back to you within like, 10, 15 minutes at the latest. But yeah, if anything pops up, feel free to send me an email.